Okay, welcome back. Oh, thank you. Welcome back. We're so close to the end. But first, we have the other stuff. Trying to jam our heads with more confusing stuff. The process that we call teaching. Processes we call warning you about things that I expect you to know and that you file away so that later you can talk about them. So we're going to talk now about SSDs in a little bit of detail. Useful to know about SSDs for a lot of reasons, primarily because the closer to users you get, the more likely the data that you're storing persistently is on an SSD and not a hard drive. If you think about the modern world, you have a desktop or a laptop here represented by a box that has an SSD inside it, very likely. Does anyone have actually a computer with a hard drive? Yeah, some of you. So it's still cheaper to get a hard drive, but often an SSD. But if you look at the data center, what we have is in the data center there are many, many machines, and in those there are certainly hard drives as well as SSDs, plus some SSDs. And the reason for that is cost. Hard drives are still way cheaper cost per byte than SSDs. SSDs are faster, as we'll talk about in a second. So therefore you think, well, why not use the faster thing? Well, sure. If you have a reason to use the faster thing, pay for it and use them. But if you're just talking about storing bytes, hard drives are still the place to store them. Think about if you talk about just even like the number of videos ingested into YouTube per minute. It's some huge amount of data. You want that to be stored as cheaply as possible, so it's stored on hard drives inside of, say, Google data centers. But yeah, higher performance things are available, and increasingly that's what you're going to see on the kind of consumer side. And of course in data centers too. Interestingly, inside of data centers, when SSDs became available, immediately people are like, oh, this is great. We can, it turns out if you look at the quarterly report, how many people look at like quarterly reports of big tech companies? So a few of you future MBAs or something. So if you ever look at those, what do you notice? It's that tech companies make a lot of money. Like they make so much money. Like how much money does what's the revenue? Would anybody know who looks at these things of like a company like Amazon or Apple per quarter? How much money do they make? Total revenue, not profit? How much money do they bring in per quarter? Anybody know? Ballpark. $12. That's about right. Yeah. What's the guess? Yeah, Intel's 10 billion, so that's kind of a medium tech company. What's Amazon or Apple, I think, reported recently? Yeah, in the back. 50 billion per quarter. $200 billion per year, growing at some funny rate. They actually don't know how to spend this money. Google, same type. Google's probably not quite that big, but pretty big. Huge. All the biggest companies in the world became tech companies. When I was growing up, that wasn't true. All the biggest companies were oil companies, right? They were all the oil companies, and they're done destroying the world. Now we're moving on to the computer people destroying the world. So that's pretty exciting. Anyway, yeah, I shouldn't talk about stuff like that. So anyway, I'll delete that later from the video. The important point there is they have so much money. So of course, companies like Google, we should just replace every hard drive. They even thought about it. We just throw a bunch of SSDs in there. They put a bunch of SSDs in their systems, and it turns out it didn't matter that much. Why is that? Why might that be? Yeah. One point is that maybe you're limited by kind of the bandwidth into the system. That's somewhat true. It kind of hints at the broader truth, I think, which is their systems actually were so well tuned to work well on hard drives that once you've spent all the engineering effort and the super expensive engineers working on things for many years, it actually works pretty well. It's hard to just replace things and make things much faster because you've already figured out how to be smart and not use hard drives in an ineffective way. So that's why it's been very hard actually for some of these places to use SSDs inside the data center. Not that they'd want to anyway from cost perspective, but like I said, what does cost matter if you're making so many billions of dollars? They could just waste a lot of money. Amazingly, they don't. They're very internally. They're in many ways. It's kind of this funny thing. Their own engineers, a lot of these places they treat them very well. Depends on the company. But then, like when a manufacturer comes in to sell some product, they're like sitting there bitterly arguing over like pennies for every hard drive they sell or SSD they sell. And I think that's this funny position for these companies that they have to, on the one hand, it's like very lush for engineers. On the other hand, they're trying to like screw everybody who's selling them anything. And they're trying to balance that. They're like, hey, come have free lunch here. Hey, we're not going to pay you any money for all the stuff you're selling us. So that is the world of the modern data center. Anyway, what are we talking about? Well, we're talking about these certain types of devices. They're called solid state devices, which just means they're something very simple. They're computer chips. This is the big revolution that's happening here with the move from hard drives to SSDs. Hard drives are very weird. Like inside of your computer, all the people that raise your hand, there's a spinning, like there's motors, it's spinning. It's like a mechanical beast. It's electrical, it's chemical, it's all this crazy stuff. And it feels kind of ancient in some ways, right? They have these spinning parts. And the disk, spins at some high rate, and it's all doing that magically inside of a tiny space now, as opposed to the old hard drives, which are huge. Now that's being replaced with just a bunch of boring-looking computer chips, which somehow people, and we'll talk about the technology, can serve as persistent memory now. Persistent memory that can survive power loss. It's persistent, or what we'll call non-volatile memory. Non-volatile. Can survive power loss. Survive. That's not true of DRAM, for example. Right? DRAM, you have to have memory power to it. In fact, you have to constantly refresh it in order to keep the bits in place. Lots of reasons for that we're not going to talk about how the technology works. Solid-state devices are not like that. So what we're going to talk about now are a particular type of solid-state device, which we'll call the flash-based, because flash was a particular technology. It was developed in early 1980s in Japan, and then over the many years has become just a kind of a consumer product. Why did it become a consumer product? Well, it was very hard to dislodge the hard drive industry, because people who build hard drives are pretty good at it, right? Just like anything where the industry is successful, they get better and better at it, figure out how to pack more and more bytes in, make it cheaper, make it high performance. But suddenly then people were carrying around, all these consumer electronics that needed storage. What was like a big example of that made a, kind of a new market for storage? Before a phone. Yeah, I know, it's all you think of these days, phones. Yeah, an iPod, right? An iPod, was like a portable computer that didn't have phone capability, for music playing. People own. You're all so young. Did anyone own an iPod? Okay, so that was like when you were 10, you had one or something like that. Do people do those still exist? Actually, I don't even know. Do they? They don't sell them. You just buy them. That's a great idea. That you can just buy them used. Okay. So anyway, iPods got created. There was a new market for storage, and people, of course, what was the first iPod? It had a hard drive in it. But that's not a really great match for a hard drive. It's mobile, it's shaking all the time. You have to kind of deal with it. You shake it, the music doesn't sound as good. So it was a natural place where the new market existed, and then there was suddenly a place for solid state to kind of come in and become a high volume product. It's important to become high volume because then you figure out how to make things cheaply. You have all these efficiencies of scale, which things they talk about in manufacturing world. We don't talk about things like that. But anytime you can manufacture anything at scale, you can do it cheaper. And if you can do it cheaper, suddenly you can be cost competitive with something that exists as a technology already. So that's what led to these flash-based SSDs. So now we're going to talk about their internals and how they work. And we're going to talk a little bit about the interface as well. And maybe we'll do the interface first. Okay. So the interface is just the same as a hard drive. Exactly the same. So it's a bunch of blocks of some size, let's say, sectors, we could call them, and then you can simply read or write those blocks. Same simple, silly interface. Why do we want the same interface? Well, it's pretty obvious. You already have computer systems which people buy that have hard drives in them. You want to be able to instead sell them this thing that looks like a hard drive to them, but just performs a lot better, right? So it's the same thing with why we had RAID systems that look just like a hard drive. We want something we can just plug into a system in existing protocols. You don't have to change anything about how they're used, and you can just immediately deploy them. So lots of reasons for this kind of sameness. It's why interfaces trap us in some way. Sometimes they make us do things less efficiently. We'll talk about that maybe a little bit today. But that's going to be the interface, the same exact boring block read or write interface that we've had since since SCSI was introduced in the 80s. So interface is going to be the same. What we're going to talk about are the internals. When we talk about flash, usually we start by talking about flash chips. So a single SSD or solid-state device, an entire device, has many of these chips inside of it. And then the chip is organized as follows. It's as follows, I guess. So we'll think of a single chip. Now this is where the terminology is going to just make we're just going to make ourselves unhappy with the terminology, because we're just going to use the terminology that comes from the people who build flash-based SSDs. And of course they use a bunch of terms that we're already used to in ways that are different than we've used them already. So here I said we kind of read or write blocks, like 4K chunks. Chips are actually organized into blocks as well. So this is a block. But these blocks are much bigger than the blocks that we're used to. So this might be, say, for example, 256 kilobytes or something like that. And this is called a block. It's sometimes also called an erase block. We'll see why that is in a second. A block, then, in SSD terminology, is chopped up into a bunch of what we will call pages. Unfortunately, that's just what it's called. And each of those might be something like 2 kilobytes or 4 kilobytes. We'll just make it 4 kilobytes for the sake of matching some sizes that we already have. So that's just something we have to remember, that a single chip, of course, again, the SSD has many chips. We're not going to really focus on that. But a single chip is chopped into a bunch of blocks. Those are relatively big, sometimes called erase blocks. And then each of those is further divided into smaller units, which are called pages. And we'll see why this is relevant in a second. Now, at the very lowest level, when you're storing like a bit in flash, what it's doing is it's essentially, and we're not going to talk about the physics of this, of course, but it's trapping some charge inside of the solid-state device, and it's being able to use that to differentiate whether, say, the bit that you're storing is a 0 or a 1. So the trapped charge is then going to indicate whether a value in one of these gates is a 1 or a 0. And how that works relates to low-level things, like you have to understand kind of device physics level stuff, which you would learn maybe if you're a double E, or maybe computer engineers would be forced to take stuff like that. We're not going to talk about that here. What we're going to talk about is we're arranging these bits. Oh, sorry, I guess I should make one other point there. We can kind of encode a few more bits in there if we want to. So for example, if we just want to have high and low charge, we can let's call it like a single level cell, because it just can differentiate 0 or 1. We can actually pack more bits in there by having like a high charge, a kind of a medium high charge, a medium low charge, and a low charge, and then associate that with 2 bits of information. Those are some different types of flash you can buy. We're not going to talk about how that works, just something you should know. But for now, we'll just kind of assume that we have these bits. The bits are organized into these pages, which are then organized into these blocks. Now here's the weird part, and you have to remember this in order to understand anything about how a flash works. Let me move up here to understand this. The operations to a flash, they're a little bit different than just read or write. And this has to do with the nature of the technology. We're just going to kind of take this on faith. So you can read a page. So any page, given an address, this page, this is page 0, 1, 2, whatever, 3, 4, etc. So to read a page, you can just read a page, and this gives you back the data. And we'll talk about performance of these things and reliability in a second. So reading is kind of like as you expect. You kind of give it an address, and it just gives you back the data there. And how that works, again, device physics, but we're not worried about that. Functionally, that's what it does for us. What's weird about Flash is how you update it. And so update is done in actually 2 steps. To make a block, an entire block, like one of these, to make it so that we can change its contents and write to it, we have to first change its state to something we call erased. So at first, maybe it's not valid, we can't write to it. And then what we do is we erase the entire block. So this is a big thing, right? This is like I said, maybe 256K or something like that. We erase a block, and what that does is it makes that block, or the pages within that block, writable. Then, in our second step, what we can do is we can program, which you might think of as the actual writing, we can program an individual page within that block. And this can then set its contents. Now that's strange. What that means is if you think of a particular block, let's pretend the block is not quite 256K. Let's pretend it just consists of 4 pages. First, what we're doing is, let's say it's kind of not valid at first, or invalid, so we can't do anything to it. Then what we do is we erase it, which then sets all of its pages to valid or writable. Let me write this down here. Invalid, not writable. Valid, which means we can write to it now. Then that's done with that erase of the entire block. Then, let's say we want to put some data in one of these pages, we can go ahead and say, let's say this is page 0, 1, 2, or 3. Then we can program a given page. Let's say we program 0 with some particular data. What that does is it changes the contents of this to be written. And now this is written, and these are still, let's say, valid, or probably better. I am using probably not the best terminology here. Let's call this just erased. Sorry, that's probably easier. I forget what I wrote down in the book chapter, so let's just call it erased. Sorry about that. And we could call written, perhaps we'll call written valid. Now what we have is block 0, 1, 2, and 3. Now we've programmed some data. And what we can do is if we can continue to program these if we want to. But then the key thing is once it's once programmed, I ran out of space here, to overwrite, you have to erase the entire block before you can rewrite any one piece of it again. So that's pretty strange. We can to write any page within a block, we have to erase the whole block. Then we can program each page exactly once. And then if we want to change the contents of that thing, we have to erase the entire block again. We can't simply just overwrite some piece of it. That's weird. So let's make sure that makes sense to us. We have a read operation. That's actually simple. Give a page, I read it. I want to write something. I have to somehow figure out how to erase an entire block and then program a particular pages within that block. If I want to rewrite them, I need to erase them again and then program them again. Yeah, question?
So when you're blowing away that block,
Yeah, great question. You're worried about like when we're overwriting something, I need to what do I do with the other contents that I actually want to keep? That's going to be a central question. So let's keep that as a question without an answer right now. Is there another question in front? Same exact question. Good double question. Other question. Make sense? I mean, we're just accepting this is how it works. To understand why that is, you have to really understand the device at a low level, but we can understand it at this level, and it's actually quite fine to understand it at this level. So let's think about what this means. Well, first let's think about there's some performance characteristics, and let's think about there's also some reliability characteristics that we need to know. So the performance characteristics first. Well, reads actually turn out to be pretty fast. You can think of them as like tens of microseconds. This is micro. How does that compare to hard drives? It's much faster, right? We have hard drives, we talk about milliseconds. Flash, we talk about tens of microseconds to do reads, which means if you're doing random reads, it's going to go way faster than a hard drive. And any of you who've ever moved to a system that uses a flash-based SSD, after using a hard drive for a while, probably you notice that at first. Eventually you don't notice it anymore and it becomes not so exciting. But there was that moment where it was interesting that you got a new type of storage system because it's much more responsive. Has anyone had that feeling where they noticed that? And it's about as exciting as life as a computer scientist gets. My computer is somewhat faster. Why? Well, it's this technology that I don't understand. So it's amazing. So anyway, yes, a lot faster, and that's true. Erase operations, which was again the first step of updating anything, these are quite slow. So you can think of these as like a few milliseconds. And again, that's milli. So that's actually kind of disk-like, right? And then program, which is the piece we need to do, this is of the whole block, which is big, program which of a small page, that's somewhat fast. So think maybe 100 or a few hundred microseconds, something like that. And people are working, and this is one of those things where the technology is moving fast enough that people are figuring out how to do things better and better, but that's a ballpark number. So that's going to have implications for us. If we're doing a lot of erases, it's actually going to mean that writing to this device is going to be pretty slow. So we need to think about that. And it also means that writes generally, it's hard to make them as fast as reads. We can, to some extent, by having lots and lots of chips, so we can make writes kind of fast by using parallelism, but reads are kind of fundamentally faster. Okay, one other comment. We talked, that's performance characteristics. Let's talk a little bit about reliability characteristics. Reliability. With disks, they were mechanical things, they had electrical things, they had chemical things, there are all sorts of failure modes. We know disks absolutely can fail. We also knew that disks, weird things could happen, they corrupt data, stuff like that. But lots of things, hard drive, head crash, stuff like that, physical things that happen. Here, there's actually a technology problem which happens, which is called wear out. And that basically, if you erase and program a block too many times, it becomes unusable. And that unusability has to do with its ability to differentiate in the bits, the specific individual gates within that, say, block of bits. It becomes hard to differentiate what's a 1 and what's a 0. And so over time it becomes harder and harder, and then eventually the drive says, I can't use this block anymore because I can't tell what are 1s and what are 0s. So if I do that too much to any one block, it's going to wear out and not become useful anymore. Now, immediately, that has an implication for us. What kind of implication would that have for a system designer, somebody who's building an SSD out of many chips, and then of course, each of the chips have many blocks, yeah. Yeah, yeah, exactly. Like if you're saying if I use this one block a lot, it's going to uh, wear it out. What am I going to try to do? I want to keep the device alive as long as possible. So it means I want to make sure that the blocks are used kind of equally. There's like what we would call a wear leveling across the blocks to the extent possible. Now, in a hard drive, we don't have that concern. A hard drive, um, no matter how many times you read or write a particular block, that doesn't change anything about that block. Certainly, hard drives eventually run out of steam and crash or stop working, but it doesn't have to do with a particular thing that you're reading or writing. With an SSD, it absolutely does, and so therefore, we're going to have to be concerned in the design of the SSD device of how to kind of keep even wear across all those different blocks instead of like say channeling a bunch of writes to a specific part of the SSD. Does that make sense? Okay. Any questions about that? Yeah. Oh well, you write all that stuff at the same time. So, you're right. It actually is a trade-off. That ones that are packing more bits in, they wear out at different rates. That's actually true. Yeah, that's a good observation. Yeah. Yeah, absolutely. Like if you happen to wear out one block, that doesn't necessarily mean the whole device is useless. It just means that you've lost some data. So you need to figure out how to deal with that. And then, eventually the device you might decide I don't want to use it anymore because many, many blocks of it are not readable anymore. Other questions? Yeah. Yeah. Yeah, I understand your question. So the question is about, hey, we have this interface to this thing. Where did I talk about interfaces? Up here. We're just using it like a hard drive, but the client of the interface is the file system. Maybe we could design the file system to kind of use the interface properly and therefore help us with this. We could do that. And so that's kind of co-design a file system and a low-level flash-based device is something people are working on and do actually do within some data centers in some places. However, if you're the manufacturer, the standpoint we're going to take is that we're the manufacturer of an SSD device, which we want to be able to use in any system. And so then you're a little bit more paranoid. You want it to be that even if the user of the system is a file system that, for example, has a superblock at the beginning or a checkpoint region, like we talked about, and is constantly overwriting that block with new information, we don't want them to be allowed to, say, wear out the device by having a bad user pattern. So we're going to be more defensive, and we're not going to trust the user. You're right, you could create a situation where you do trust the user of the device, and then kind of have a different relationship between those two pieces of software and then, I guess, hardware here. But generally, we won't do that, because if you're selling a consumer device, you want it to be robust no matter what if it's a bad Windows file system or a bad Linux file system that's doing something strange, you don't want it to be that it immediately wears out like the most critical block and then becomes unusable, right? Like, so you talked about wear out before. The exact blocks that you write a lot are things like, oh yeah, maybe we write the super block a lot. And if we can't read that, then we can't read the file system anymore. So we have to be very careful of that sort of thing. Good question. Yeah. Yeah, that's a great point. Not only is when you're talking about cost in a data center, you're not just talking about the cost of initial purchase. You're talking about the cost of maintaining bytes on that device in perpetuity. So if a hard drive replaces every 5 years, but SSDs wear out every 2.5 years because of this wear out problem, that will essentially double their costs even compared to their initial purchase cost. So yeah, you absolutely have to take that into account. Where would an SSD then actually be quite effective is places where you, for example, write the data once and then only read it afterwards, right? And then reads don't really hurt our kind of wear out, so that's maybe extends the lifetime of the device quite a bit versus data that we're constantly rewriting. That has a different property. So it probably depends on the workload. much more than a hard drive, which is much more workload insensitive. But that's an excellent point. The analysis that you'd have to do to understand hard drive versus SSD is more complex and includes understanding the workload as well as this kind of long-term replacement cost. Really good point. Okay, so all we're going to try to do here is then understand, given this basics, that we have an SSD, like we'll just kind of assume we have one chip which has a bunch of blocks. Each block has a bunch of pages, and then the way we read those pages is easy, we just read them. But the way we write is strange, that we erase a block to kind of make it writable, then we can program each page exactly once, and then if we want to reprogram that page, we need to erase the entirety again and then reprogram it. So what we need to do then is what we were trying to do, and we of course have to take into account these performance characteristics where erase is expensive, we don't want to do it a lot, whereas reads and programming is generally kind of fast. So what we're trying to design is an entire device, an SSD, a solid state device, which is more than just a bunch of flash chips. So you can think of our device like this. It has some sort of microcontroller, like it has an interface to the system, right? So it has some sort of interface where we can send reads and writes to it. Internal to there, it has some sort of maybe like a little CPU of some kind, which is running the software that runs the device, or firmware we might call it. It might also have some memory because it's useful to have volatile memory in there to maybe cache some little things and so forth, and of course our CPU would run out of that. And then we have one or more flash chips down here, flash 0 through whatever, n minus 1. And what we're trying to do is build this layer of kind of software that allows us to manage the data and how we map it onto these flash chips in an effective and reliable way so that we don't wear out the device and we get good performance. So that's what we're going to try to figure out. Sometimes people call this software that's running here, they focus on one piece of that, which they call the flash translation layer, or FTL. And the FTL is going to be responsible for, it takes reads and writes to the interface, right, just to block 0 or block 1 or whatever, and then it has to map them into low-level flash operations, which are, like we said, reads of pages or erase and programs in order to update things. Erases and programs. So that's what the SSD device looks like, and inside of there, that FTL that we're going to design or talk about how to design is going to take those reads and writes and then figure out how to map them onto the operations that each flash chip gives us. Okay, that's the challenge, and actually that's the last technical challenge we're going to have in this class. Is just to understand that a little bit. Well, I mean, we have a bunch of stuff to do still, so don't get too excited. But that's the last thing technical challenge we'll try to overcome in the lecture, is that. So that's a little bit easier, I guess. So that's the FTL. So you've probably heard that when people talk about SSDs, they often talk about the FTL and what's the FTL doing. But that's really just they're talking about what's this software that's managing the translation of logical operations to the physical operations that the device permits. Okay, logical reads and writes to the physical reads, erases, and programs. So any questions about that generically? Kind of make sense? Okay, let's see if we can make a little bit of sense of how this is going to work. Here's a bad way to do it. Bad way to build an FTL is what I'll call like the direct mapped approach. So in this direct map approach, what we would do is here's our device, which again is chopped up into blocks, and the block is chopped up into pages. So this is block 0, this is block 1, etc. And let's say these pages happen to map exactly to like a file system kind of block size, right? That's confusing. Logical blocks, 4K. So, but these are, again, this is like page 0, page 1, page 2, page 3. What a direct mapped approach would do is it would just say, well, logical block 0 maps, so logical block 0 maps exactly to physical page 0. Logical block 1 maps directly to physical page 1. Logical block 2 maps to physical page 2. That's the direct map approach. And a read, therefore, in this approach is really easy because you just read at the given address. Right? It's just the direct mapping of the blocks that are available. You just can read them. And if that's all you were doing, actually, this would work really well. You don't have to keep a lot of information because the mapping is so simple. Everything's good about it. The problem, of course, comes with writes. So reads are easy. Let's say somebody wants to write, let's say, address 2. So this thing right here. What would they have to do? What are the steps? Actually, why don't you think about this? This would be good because it's probably good for me not to talk so much and you just think a little bit more than what happens if I'm just talking too much. So just think for 1 minute. If I have a direct map system, I want to update the contents of page 2 like I've shown here. What do I have to do? And you know your operations that the flash chips provide, which are for writing, erasing blocks, and then programming pages within those blocks. So think about that for 1 minute. Feel free to talk, and then let's come back and discuss it. Okay, why don't we talk together? So what should we do here? What's the process? What steps should we take? All we want to do is update this little page 2 here, lying on the device. What should we do? Yeah. Yeah, that's what you would do. So what you would do is exactly that. If we just say, hey, we want this direct mapping, that's all fine for reads, but for writes it means, well, we're going to have to erase the block. So it means if there's anything in there that we care about, for example, we care about P0, P1, and P3 in this case because we're just updating P2, we'd have to read those say, into memory of the device. We could read them into the memory of the device. Now, if we just read them into memory, we have a problem. If we lose power, we actually lose all of that data. So we might want to even write that out somewhere else. So that's expensive. Let's not think about that for a second because that's even worse. Then we can go ahead and erase this entire block. That then clears the block and makes it all writable. So it becomes something that's erased and we can write to it. Then we go ahead and reprogram this old data plus the new version of P2, which I call P2 prime in this case. So that sounds pretty bad. It has a number of performance problems. It's mostly that it's slow. That's a kind of a primary performance problem. It's really slow because each program, just one write turns into an erase and many reads and program operations. So it's really, really slow. It's like hard drive kind of slow. That's bad because remember, erases take milliseconds. It also has the problem, well, it has a reliability problem, which is that if somebody just simply writes a particular block, logical block over and over again, that's going to erase the same physical underlying block over and over again and quickly wear out, right? So wear out is not under the control of the device, it's under the control of the usage pattern. That sounds like a bad idea. So it's slow and it wears blocks out really, really quickly. So pretty obviously when people started building flash-based SSDs, they realized it was not workable to have this kind of direct mapped approach, which you might expect as a natural approach for a storage device. Like with RAIDs, remember when we talked about building RAID storage systems? We just had a very static mapping of like striping data, 0 goes to disk 0, offset 0, block 1 goes to disk 1, offset 0, etc. Very static mapping. A hard drive has a static mapping, more or less, of logical blocks onto a particular platter and track and sector within that track. All those are very static. That means you don't have a lot of information about where things are because it's a very easy thing to kind of encode in a static way. Here, that doesn't work at all. It just will cause things to run slowly and to wear out. So, what are they going to do? One is just use hard drives. So, forget about flash. It was a great idea until I tried to use it. The other is to be smart and design a better FTL. Smarter FTL. What might we do? How might we make writing efficient? What ideas do we have about writing that might help us in this case? Yeah. Well, buffering, sure, that helps, yeah. Yeah, better with logging. Same idea, amazingly. What we're going to do is we're not going to update things in place. We are going to do this kind of copy on write. Every time we write something, we're going to write it to a new location and keep track of it. So that's what modern FTLs do in lots of different variants. Let's just get a basic idea of it. Some of the ideas, it's actually kind of fun to talk about LFS and SSDs in the same breath or the same lecture because they have some underlying similarities in how they work. And specifically what we're going to do here is inside the SSD, so we have our SSD, we're actually going to have, let's say, a fair amount of memory. And in the memory, what we're going to do is we're going to have a map, and the map is going to tell us for each block essentially where the last version of that block is. Okay, so this is very similar to our inode map, but here it's for blocks that we're writing. So what does that mean for the device? What does it mean to write, do a logical write? What it means is this. We have, here's our blocks, like this. That's chopped into pages. So this is block 0, block 1, block 2, block 3, etc. And again, this is page 0, page 1, page 2, page 3, etc. When we're doing logical writes of, say 4K in size, what we're going to do is just basically start at this side of the device and fill it in going like this. So do log style writing. This is one big log. Why do we call them logs? I guess I didn't even talk about that. Just the log is something you just append to. Append is kind of the interface to a log. We're just adding to the end of the log is how we always do things. Which means the first time we get to a particular block, what we do is erase the block once. Then what we do is we just start programming in pages one at a time. And down here, I'll keep say, is record in memory. In the FTL is what people would say. In the flash translation layer is actually just this map. Record there the logical block, which is what the interface says, to physical page mapping. So let me do an example there. So let's say the stream of writes that come from the user, let's say they write block, let's say 100, what looks to them like logical block 100, and then that has some data in it like, I don't know, like A, it's full of A's. Then they write 101, and let's say they put B's in there, etc. What we're going to do is simply, well, first we'll erase this entire first block because we're first starting to write to this device. Once it's erased, we can go ahead and record this first write there, A. Then we can record this second write here, B. Now these are programmed. And then in the mapping table that we have in the FTL, what we're going to record is that 100 is in page 0 and 101 is in page 1. It's really as simple as that. And if we keep writing, you can imagine, then let's say the next write that happens after that is, let's say we write to a completely different block, logical block. Let's say we write to block 200 and we write the contents C. Well, we would write C here, and then that's become programmed. Remember, we have to erase it before we ever do it again. And then we record in our table 200 is at physical page 2. We just have a table in the memory of the device, and if you're using an SSD, they have a table like this. It's the FTL, and that's all it's doing. It's saying for anything that you wish to read, you first have to consult this table that tells you the location of that on the device itself. And all the same problems that we had inside of the LFS happen here too, which means when we overwrite something, let's say we now, then later we write, much later, let's say we write block 100 again and we fill it not with A anymore, but with a capital A. A pretty exciting workload pattern. Let's say we were writing to this block at that time. That might put the capital A in here. Then this thing becomes, programmed after that whole thing has been erased. And then the FTL, of course, because we've written to logical block 100, now records not 0, but whatever this is, 4, 5, 6, 7, let's call it 8, page 8. Let me just go ahead and erase this now. So very simple idea is you just erase when you're writing, you just erase things once, then program them one at a time until you fill them up, and then you move on to the next free block, and keep going from there. Same problems as before. It's constantly trying to erase something. Problems. Well, there's actually a few problems. One is old. This is an old problem. We saw this before. Garbage. Absolutely the same problem that we had before. A bunch of old stuff fills up these blocks. We have to reclaim them. And the reclaiming is done exactly in the same way that we did before. How do we figure out if things within this block of the device are live or dead? Well, we read them all in, and then we look to see, hey, is there does anything in the FTL refer to this? Is there a pointer to this? Is there a reference to this in the FTL? If there is, then it's live. If not, then it's clearly not. So garbage collection I won't talk about anymore because it's kind of like what we've already talked about with LFS. There is another problem which you might be worried about, and just because of time's sake, we're not going to talk a lot about it. It's something that people in FTL design spend a fair amount of time on. It's written about a little bit more in detail in the book. What other problem can you see with these mappings? Yeah. Oh, sure. We have the kind of old problem there too, right? Which is so that's true, and I should write that down. Is we need to figure out how to how to recover the FTL, the translations, after a crash. So that's true. That's a problem. Sometimes we just write a little bit of information down with each little block that we're writing, and then like the cheapest SSDs will just scan the whole SSD and figure out the mapping information from that. More expensive ones will kind of checkpoint the mappings periodically so they can recover them more quickly. But yeah, absolutely same problem there too. When we're updating mappings, eventually we want to reflect that to the disk and make sure that we can recover it. But what other problem would we have? What's a new problem that seems a little bit different? A new problem that's different than LFS. Yeah, what's your guess? Yeah, that's absolutely one problem. New problem is where leveling. What? Why does this kind of log structure? I'll get you in a second. Does log structuring kind of do where leveling for us? Does it make sure that how much each block is erased and written is kind of even? Any thoughts on that? Yeah. Well, that's true. If you're anytime what you said is like anytime you have to update something, you're kind of moving it somewhere else. That's just the cost we're paying. And where leveling, logging does kind of do some where leveling because it's spreading writes across. But you could write some block once, and then the data in it is never rewritten, and therefore you never free up that block. Therefore, it's never being written to. Therefore, where is being spread unevenly. So what do you need to do to where level is no matter what, periodically, you have to go through the device. Even if data is perfectly live within a block, you have to read it and write it somewhere else and then erase that block and make sure the erase load is equal. So there's some extra work beyond garbage collection. If you want to really do where leveling, it implies that you're, even for blocks that are full of live data, you are going to read them out, move it somewhere else, and then erase that block. So that's one new problem. We have to do this in the FTL in order to keep where even. There was one more comment over here. Yes. Great. Question over here. Bytes. Yeah, that's a great question. The question is about the atomicity guarantee of the device. Because people are trying to build a device that's compatible with, basically is a stand-in replacement for hard drives. That means they're trying to match that guarantee of a 512 byte write is an atomic write and bigger may not be. In practice, somewhat larger writes may be atomic because of the nature of how the device works. And in fact, some kind of more researchy things, people take advantage of that and do even kind of get some larger scale atomicity guarantees out of FTLs and SSDs. But yes, minimally they're going to try to say we have the same guarantee as the hard drive. Is there a follow-on question or just curious? Yeah, okay. Okay, yeah, so that's a great question. One other new problem that we have to worry about here, compared to, and really the last problem we'll talk about, compared to log structure file system. For the log structure file system, which we just heard about for the first time, we had an inode map, which means the number of things that we were mapping, that we had this indirection on, is ordered the number of files in the file system. So in a very large file system, sure, you might have millions of files, but that's with maybe billions and billions of bytes. Here, how big is the FTL? Here, remember, let's look at it right here. How big is the FTL? Answers, somewhat big. Getting ready for a multiple choice final. Pretty big. Actually kind of big. Big. Really big. Way too big. That's what the whole final is going to be like. A bunch of vague answers that overlap. Therefore, you're either always right or always wrong. FTL, how big is it? How can we compute how big it is? Let's say we have a terabyte SSD. Anybody have what's a big SSD people have? Like 512? You can get a terabyte one now. Terabyte SSD with per page mappings. Let's pretend for simplicity that a page is 1 megabyte. Okay, maybe it's, sorry, not 1 megabyte, 1 kilobyte. Sorry. Let's pretend. So how many mappings? Well, mappings. How many mappings do we have of logical blocks, what we call logical let's call it 1K blocks for simplicity, to 1K pages? Well, it's this divided by this. So how many mappings are that? That's a lot of mappings, right? It's kilobyte goes to megabyte goes to gigabyte goes to terabyte. So that's, on the order of like a billion mappings. So if that's true and each one is, say, 4 bytes, how much memory do you need to have in this device to hold all those mappings in the device memory? Well, way more memory than you want to have in a device, right? That would be the most expensive part of the device, would be its memory, be like gigabytes of memory. So clearly, the FTL, we have to figure out, one goal in design is to not need all those mappings all the time in device memory. So what are you going to do in the device? You remember the device when we looked at it up here. It has memory, this map, or the translation layer has to live in the memory of the device. It tells us where every logical block is mapped to. What could you do to reduce the size of that table? Yeah. Yeah, you could do a more. All the answers are kind of the same. It's just there's some differences, right? So one thing you could do, solutions, is to have a better structure. Sure, better data structure. That could help. Then what you could do is you could only keep active pieces of the map in memory. So devices will, what do we call this in the OS? When we're only keeping active pieces of things in memory. Sometimes we call it caching. Sometimes we call it, depending if it's in the VM system, we might even call it kind of a swapping of sorts. But yeah, caching is really the right caching of those things. And then what other thing could you do to reduce the size of mapping table? What else could you do? Yeah. Yeah, you could kind of increase like what each pointer, how much it points to, right? So what in fact some people do is they use block mappings where they can, which refer to entire blocks, not pages, at once. Now that turns out to be, there's a lot of detail to that, which if I got into now would just make everybody weep. So I will leave that to you to discover on your own how that works. There's a bit of machinery there, how to use block mappings. Block mappings, of course, mean that if you look at this structure, I'll get back to it. It means you can point to one pointer kind of to refer to all the pages within this block instead of having pointers for each page. There's some complexity to that, but that's exactly what happens. So that is a very brief whirlwind tour through how an SSD works. As you can see, it's a lot different than a hard drive. It's a solid state thing, not a mechanical thing. It's much more performant, especially reads, and if you're careful, writes. It has a much more complexity in some ways because the complexity comes in this mapping, right? You cannot just do this direct mapping. You have to have indirection in there in order to manage wear and to manage performance. And interestingly, because of some of these things we talk about here, when you're only keeping, say, active pieces of a map in memory, and then other ones you'd have to like go to the device to read in the map in order to be able to, say, read the block of data that you're interested in. What does that mean in terms of like locality? Does locality matter in the workload pattern that's accessing an SSD? Why would locality matter? It does matter. Why does locality matter? In a hard drive, it matters because keeping like nearby blocks, accessing them, does shorter seeking. In an SSD, why does locality matter? It's a guess. Yeah, thank you so much.
Because you don't want to have to erase or program.
Well, that's Well, writing, you're kind of stuck, right? But what about reading? What about reading? Why does locality matter on reads? Yeah. Yeah, it means that the number of mappings we need to keep in memory is reduced, and we don't have to go to the device to get the mapping in order to read the data, right? So keeping that table smaller is what locality gives us. And so therefore, and then doing large amounts of like I/O at once means you have locality, which means to use any device effectively, whether it's a hard drive or an SSD, doing large I/Os that are contiguous always does better than randomness. Now, random reads on SSDs are quite a bit better than hard drives. There's no magic to that. But locality improves performance, and sequentiality is always the highest way to get performance out of either type of device. Okay, so why don't we do this? We're going to take one last break, and then we're going to talk some maintenance stuff and for class, and then end class with a dramatic, what did I promise? Words of wisdom. So give me a couple minutes. I'll figure out what those are.